Hi everybody. Today we're going to be learning section 11.8 on power series. Okay, so first we need a definition of what this term means. So a power series is a series of the following form. It looks like this: n equals 0 to infinity of Cn x to the n. What does this look like? Let's actually write out the terms, okay? So the first term would be C naught. The next term would be C1 times x. Plus the next term would be C2x squared. Plus, you can keep doing this, then we get Cn x to the n, and it just keeps going forever and ever. And of course, every Cn here is a real number for all n, okay? So what is the difference between a power series and a series that we've been looking at? You notice the main difference here is that there's an x, okay? In other words, it has a variable in it. This is brand new, right? Every series we had before only had n, but now we have n and x, okay? So what is this then? A power series can be thought of as a polynomial of infinite degree. Of course, there's no such thing as a polynomial of infinite degree, but that's the whole point. Is if you take the idea of a polynomial, except you keep getting higher and higher powers forever and ever, this is what a power series actually is. Okay, so what is the difference between them then besides that? Well, another way we could think about it is that a series if it converges, it equals a number, right? It equals some number. Whereas a power series, which looks like this is equal to a function, not a number, right? It's a function because it does not actually have, well, I should say it's a function because it has a variable in it, right? So you could still plug in something for x at the end. Okay, so one of these guys is a number. What you've been dealing with before, a series, you can think of it as a number if it converges, right? Whereas a power series is a function. Why do we say that it's a function? Well, notice something. So notice, what happens if we plug in a value for x in a power series? If we plug in a value for x in a power series, it becomes just a series. And so every series either converges or diverges. So I'll say that it becomes just a series which may or may not converge. May or may not converge. Okay, so because it converges for some x's and it does not converge for other x's, the way you could think about it is that by plugging certain x's in, you get a value, and other x's that you plug in, you do not get a value. But that sounds a lot like the word domain for functions, doesn't it? So, I should say, if we let f of x be a power series, then the domain of f is the set of all values of x where this guy converges. Okay. Before we do some examples here, I want to point out something. Notice that our series is now starting at n equals 0. This is because in a polynomial we do want there to be a constant term, right? So because we're indexing by using the powers, we need to start at n equals 0 instead of n equals 1. But remember, that's not going to affect convergence or divergence, right? That's just adding one more term. Okay. So let's do a quick example here. So number 1, consider the power series f of x is equal to x to the n. Note that this is a power series because it has an x to the power of n in it, right? You'll notice that this looks like, if we were to write out the terms, it looks like this. So question, what is the domain of f? Okay, so where does this thing converge? That's what we need to look at. So what kind of series is this? Now I know we have an x which we're not used to, but remember x just stands for a number, right? So if we look at this series, isn't it true that we see a pattern here to get from 1 to x squared to x cubed? Isn't this a geometric series? So notice this guy is a geometric series. Which converges if and only if the absolute value of its ratio, which is what in this case? Well, if you look at the terms, each term is getting multiplied by x, right? Times x times x. So it's clear that the ratio is x. So it converges if the absolute value of x is less than 1. Okay? But that's exactly the x's that sit between -1 and 1. So those are the ones that it converges for. And so the domain of f is that set right there. Okay? All real numbers between -1 and 1, not including -1 or 1, because that would be a ratio of exactly 1. Okay, let's go a little bit more specific with our definitions here. A power series, we're going to get even more specific, centered at 0. Or centered at A. Is a power series of the following form. Now notice instead of saying x to the n, it says x minus a to the n. So what do these terms look like? So this is what it looks like. Instead of raising x to various powers, you're taking x minus a and you're raising it to various powers. So this is what it means to have a power series centered at A. We're going to learn later in this section why we use the word centered for this. Okay? What do we say about A? Where A is a fixed real number. Okay, so you can have a power series centered at any real number that you want. So note, the power series that we were studying before is really this, isn't it? We really had an x minus 0 there that we weren't mentioning. So the guy from before is a power series centered at 0. Okay, so before when we just called it a power series, it was really a power series centered at 0, right? When you have it 0, that just looks like a regular old polynomial that you guys are aware of. So what we're going to be concerned with is the nature of the convergence of power series, okay? What does it look like? Let's think about these things a little bit. So note, I'll call this note, okay? So note, a power series always, no matter what, converges where? So what I'm about to write down is important because a thing you might wonder is, if I write down a power series, is it always guaranteed to converge somewhere? Or is it possible to write down a power series that doesn't converge anywhere? It turns out it always does converge somewhere. Where does it always converge? At its center. Why is that? Because at its center, if you plug in A, what happens? Well, if you come back up here, all of these terms are actually going to go away and become 0. And so you just get the constant term, C naught. So of course it converges, right? You don't even have an infinite series anymore. You just have one term. Okay? So it always converges at its center. That's the first thing. We only remain with one term. Okay. So that's the first thing. Now the second thing. Okay? This one's important. Of course, it converges at its center, but the question is, does it converge at another point? Is it guaranteed to converge at another point? How can we tell? So, here's something important. We can always the ratio test. So we can always use the ratio test. To see when a power series converges. Why do we know we can always use the ratio test? Well, we're going to actually show why this is true. Okay, so suppose we use the ratio test on a power series on that guy. Now remember the ratio test. The test says that we need to take the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term. So it's going to look like this. The n plus first term divided by the nth term. So it looks like that. So what does this look like? Well, let's actually do a little bit of math here, okay? We're going to pull, so first thing we notice is that we have an x minus a to the n plus 1 and an x minus a to the n. So we're left with a single one of these x minus a's, right? And notice that has no n's in it, so I can definitely pull it out of the limit, right? So we end up with the following. So when does this converge? Let me go ahead and give this a name. Let's go ahead and call this L. So the question here is, when does this converge? We know that the ratio test says that the power series converges if L is less than 1 and diverges if L is greater than 1 and no info if L is equal to 1. I just want to throw that in there just to remind you that if the limit is exactly 1, we get no info from the ratio test. It might converge or it might not. So what we are concerned about then is this, okay? What can happen? When is the limit less than 1 here? Remember, guys, limit is this entire thing right here, right? This whole thing is the limit. But in that limit, we have this part right here, and this part is important. This limit right here will determine whether this thing is less than 1 or bigger than 1 everywhere or nowhere or somewhere, right? So here are the cases for this limit, okay? It's possible, let's talk about this this mini limit here that I just highlighted, okay? So there are 3 cases. Either that limit is 0, or it's infinity, or it's somewhere in between, right? So, case 1. If L is equal to 0, right? If that highlighted part is 0, then the whole limit is 0. So if L is equal to 0, then the power series converges for all x. This is the nicest case. Okay? Case 2. If L is equal to infinity, what happens when the limit... So, okay, let me not write if L is equal to infinity. What if the highlighted part is equal to infinity? If that limit is equal to infinity, then does that mean that the series diverges everywhere? Well, not exactly, because remember, we still know that this guy has to converge at the center. But what we're saying here is that if that limit goes to infinity, then that means that this limit diverges everywhere except for the center. So let me just write then the power series converges only at x equals a, which is its center. Case 3. This is the most interesting case, okay? What if the limit as n goes to infinity of Cn plus 1 over Cn is equal to some number, okay? Let's just call it m. And let me say that this guy is both greater than 0 and finite. If we get a positive number that is not 0 or infinity, then what does that mean? This means that L, our limit that we get, is equal to this times this. So what is this going to mean? This is actually going to mean that this guy, so by the ratio test, it only converges when that limit is less than 1, which is equivalent to the absolute value of x minus a is less than 1 over m. So what did we just find? We found that this is convergent at some interval about a. Okay, because what this actually means, what this guy means right here is that negative 1 over m is between x minus a and 1 over m, or x is between a minus 1 over m and a plus 1 over m. Okay? So what does that mean? This means that we converge only when we're at some radius about a. And remember, a is the center of the power series, and so now we kind of start to understand why we call it the center. So this leads us to a theorem. Extremely important theorem that summarizes all of power series, okay? For any given power series, centered at A, there are only 3 possibilities. First, the series only converges at x equals a. Sorry, I called this case 2 before, but I want to list these in a particular order. I believe this is the order listed in the book. So, case 2. The series converges for all real numbers. And the third case, there exists a positive number r such that the series converges when x minus a is less than r and diverges when x minus a is greater than r. Okay. Let's draw a picture really quick of these 3 cases. If it only converges at a, then I can draw a right here. That means we only converge at that one little dot, right? Now, what if it converges everywhere? Well, then I can color in the entire line, right? Converges all over the entire thing. Finally, this is the most important case. For case 3, what we're saying is that there exists some r sorry, I wrote that wrong. It shouldn't be r here, but it should be a plus r and then a minus r. In other words, r is this distance right here. So what we're saying from this is that we only converge in that little window right there, and we diverge everywhere else. Okay. So I'm hoping that we see from this illustration why we call A the center of the power series. Notice for all 3 of the above pictures that A always sits at the center of our picture, of our convergence interval. Okay, so this is why we call A the center of a power series, because the series will always converge at A, and it might converge everywhere else or nowhere else or some number away from it, but it always sits in the middle of where it converges. Okay. So let's give a definition to this area that I shaded in, right? Wouldn't that area I shaded in, we could call that the domain, but we actually have some more specific names for these things. So this guy that I called R, we have a special name for that guy first, so let me give that a name. In case 3, we call r the radius of convergence of the power series. Radius of convergence of the power series. Sometimes I will abbreviate it with ROC. Okay, radius of convergence. By convention, in case 1, so let's go back to case 1. Case 1 is where it only converges at A, right? So we could think of its radius of convergence as being 0. So in case 1, r equals 0. And for case 2, since it converges everywhere, we can think of our radius as being infinity. R is equal to infinity. Okay, so these are the three cases. Case 1, either our radius of convergence is 0, and it only converges at the center. Case 2, either that means that it converges everywhere, and so our radius of convergence is infinity. Or case 3, the radius of convergence is actually a positive finite number, like 3 or 1/5 or something like that. Okay, we have another important definition. We have something called the interval of convergence. So the interval of convergence, which we also abbreviate with IOC of a power series, is the interval that consists of all values of x for which the series converges. Okay. So, okay. Let's think about case 1, okay? Now that we have the IOC here, I want to write down the different possibilities, okay? So in case 1, remember case 1 is for the radius of convergence to be 0. And so what would the IOC be? Well, there is no interval if the radius is 0, right? Think about it. This means that we only converge at A. So we don't really get an interval. That's the one case here where we don't get an interval. So the IOC is just equal to the number A. Case 2. It's not that R is here. So yeah, case 2 is that R is equal to infinity. What would the IOC be? Well, then this means it converges everywhere, right? That was case 2. And so the IOC would be all real numbers. Or if we want to write it in interval notation, we can. It's just from negative infinity to infinity. Finally, the most important one, case 3. Or I should say the most interesting one, right? This means that R is greater than 0 and finite. In other words, R is just some number. And so what would the IOC be? Well, if we look back here, we know that x has to be between a minus r and a plus r in order to converge. So we're going from a minus r to a plus r. Now, am I going to put parentheses around this or not? Well, we haven't talked about the edge cases yet, right? So question. Or if you look, I wrote very carefully, I said it converges when this guy is less than r, and it diverges when that guy is bigger than r, but I never said what happened when it equaled r. So in other words, what happens here and what happens here, right at the edge? Well, let's go back to our ratio test, right? If we look at the ratio test, we actually said that if that guy was less than 1, it converged, right? But remember, the ratio test says that when it's equal to 1, we get no information. And that's exactly when this is going to happen, right? When x minus a is equal to this, then this means we get no info from the ratio test. And so, what does that mean? That means that at the edges, we do not know. So there are actually 4 possibilities here. What are the 4 possibilities? The 4 possibilities are that we maybe don't converge at either one. In other words, it diverges at the edges, or it converges at the left edge and diverges on the right edge, or it diverges at the left and converges on the right, or it converges on both edges. So what does case 3 tell us? So in case 3, we must test x equals a minus r and x equals a plus r individually using a different test, right? We know that the ratio test gives no information, so this is an extremely important byproduct of case 3. What we're saying is that when case 3 happens, the ratio test is not enough to finish the problem if it's asking us for the interval of convergence. We need to do more work, test each side using a different test in order to figure out whether it converges or diverges at those numbers. Okay? So I know we just talked about a lot of stuff. I want to do several examples now where we actually find the radius of convergence and interval of convergence of the following series, or the following power series. So I'll say for the following examples, find the ROC and the IOC of the power series. Okay. All right, so let's go ahead and do that. Let me go ahead and write down our first example. So problem 2 is going to be the power series n equals 0 to infinity of n factorial x to the n. What I would do is right away write down the center. The center of this power series, of course, is 0, right? Because we have x to the n here, right? We don't have x minus or plus something to the n. Okay, so first things first, we always start, so always begin with the ratio test. So we're going to do the limit as n goes to infinity of the absolute value. We're going to plug in n plus 1. And we're going to divide it by plugging in n. So we want to see where this thing is less than 1, right? So let's go ahead and simplify here. I notice that x to the n and x to the n plus 1 leaves us with a single x on top. And what's n plus 1 factorial divided by n factorial? I'm hoping that in the ratio test section you guys were able to practice some of the factorial problems, but n plus 1 factorial over n factorial simplifies to n plus 1, right? And so what does this equal? This is equal to the following. I'm going to pull the absolute value of x out, and I end up with the limit as n goes to infinity of n plus 1. You'll notice I left out the absolute value. That's because n is going to infinity, so of course n plus 1 is always positive, right? So what does this limit equal here? This limit, of course, is infinity, right? Which is greater than 1 no matter what. So what does this mean? This means that the power series, we only converge at its center at x equals 0. So this means that the ROC is 0, and this also means that the IOC is just the number 0. That's it, right? So this was what we called earlier. This was case 1, right? This was case 1. Okay? So this is what case 1 looks like, right? It diverges everywhere except for the center. Let's do another example. Okay. Let me write down number 3 here. So number 3 is going to be the following series. You'll notice n is starting at 1 this time, and that's because we have an n on the bottom, right? We can't start it at n equals 0 because otherwise we would have no, we would have an undefined term for our first term. Okay, so we're going to begin with the ratio test, okay? We're going to do the limit as n goes to infinity of the absolute value of x minus 3. Remember, plug in n plus 1, and then divide it by plugging in n. In other words, multiply it by its reciprocal. So this is what we get, and we need to see how this thing simplifies, right? We need to take this limit. Let's be careful here. X minus 3 to the n plus 1 over x minus 3 to the n leaves us with an x minus 3. What about n over n plus 1? That part's going to stay in the limit. So this is what we get, though. We can pull the x minus 3 out. Do not forget the absolute value, because remember, x can equal any number. So we take out absolute value of x minus 3, and what we have left is the limit as n goes to infinity of n over n plus 1. You'll notice I left the absolute value out of this part because the absolute value of n over n plus 1 is just itself when n is going to infinity. Right? These are all positive numbers. Now, what does this limit equal to? Of course, let's do our dividing by n trick on both to take this limit. This is going to equal the limit as n goes to infinity of 1 over 1 plus 1 over n, right? This guy goes to 0, so this entire limit is 1. And so this is just equal to the absolute value of x minus 3 times 1, which is just itself. So what does this mean? So by the ratio test, it converges if the absolute value of x minus 3 is less than 1. And it's going to diverge otherwise. Okay? As soon as you get an inequality like this with the x minus 3 isolated, this guy right here is our radius of convergence. Okay? Because remember, the radius of convergence, if we come back here, our radius of convergence is defined to be the r of case 3, right? And so it says x minus a is less than r. So that would be the case that we're talking about. Okay, so this is where we are. Now, what about the IOC though? IOC is going to be a little bit trickier. We need to start by turning that inequality, turning that guy into an inequality that looks like this. So this is how you get rid of an absolute value, and this means this is the same as the interval. If we add 3 to all of these, this is the same as the interval 2 is less than x is less than 4. Okay? So what did we just find out? We just found out that it converges between 2 and 4. However, we need to figure out, let me write that later, okay? We need to figure out what happens at the edges. So let's do the edge cases separately. So first edge case, let's do x equals 2. What do I get when I plug x equals 2 into the original series? If I plug x equals 2 in there, I end up with 2 minus 3, which is negative 1. We get negative 1 to the n over n. Okay, we have already done this problem. This was actually a problem that we did in our first example in the alternating series test. This guy converges by alternating series test, and I want to say see example 1 in, let me see, I believe that was section 11.5, right? Yeah, 11.5. What about x equals 4? If I plug 4 in, we actually end up with 1 to the n, which is just 1, so it's 1 over n, and we know that this guy diverges. Remember, this is the harmonic series, so we're allowed to just say that it diverges. Okay? So we tried the two edge cases. It converges here, and it diverges here, so we're ready to write down the IOC. Let's first write down the ROC. The ROC is 1. And what's the IOC? Well, we're going from 2 to 4, but we converged at 2, and we diverged at 4. So there we go. That would be the interval of convergence. There you have it. So this whole problem, we actually practiced doing which case? Remember, this was case 3, right? So this is case 3. You never know which case it's going to be until you actually work out the problem. Okay, let's try another one. It's going to be number 4. We're going to find, we already know what we're doing. We're finding the radius of convergence and the interval of convergence. This one actually has a special symbol, J0 of x. This is actually the series that looks like this. It's going to look complicated, but you're actually going to see that this problem is not difficult, okay? Negative 1 to the n, x to the 2n, over 2 to the 2n, n factorial squared. Okay. This is a famous function. This is actually called the Bessel function of order 0. Okay. All right, so again, start by using the ratio test, okay? So we're going to do the limit as n goes to infinity of the absolute value of, so plug in n plus 1. Now what about the negative 1? Do I have to bother putting it in there? I don't have to, because I know the absolute value of negative 1 is just 1, and so it's going to go away, all right? So don't worry about it. There's no point. Now, what do I get here? I have to replace the n's with n plus 1, right? It's n plus 1 factorial squared, and then multiplied by its reciprocal, right? So we're going to have 2 to the 2n on top, and then n factorial squared on top, and then on the bottom we have an x to the 2n, like that. Okay, we're going to write this step by step, okay? Let's start with the x's. You notice we have an x to the, what does this become? This becomes 2n plus 2, right? And this guy becomes 2n. So if you cancel x to the 2n with x to the 2n plus 2, we're actually left with an x squared. And that's going to come out of the absolute value. Why? Because x squared is always positive. So we don't actually need the absolute value there. What's next? Let's look at the 2's. You notice we have a 2 to the 2n on top and 2 to the 2n plus 2 on the bottom. So how many 2's do we have left? We're going to have 2 2's left on top, or sorry, on the bottom. And so that's a 4. 2 squared is 4, and so that's going to go down here. I'm pulling all of these out of the limit, right? I only have to leave stuff in the limit that has an n in there. What's left? Okay, this is important. We have an n factorial over n plus 1. Remember, n factorial over n plus 1 factorial is the same as 1 over n plus 1. Okay, so of course, taking this further, if we square this, it's the same as squaring this. And so since they're both squared, we know that we actually have in the limit is that. So this is the limit that we're doing. And notice that as n goes to infinity, this whole limit is actually 0, which is less than 1 for all x. What does that mean? Let me not use an exclamation point because it might look like a factorial here. So this means that it converges everywhere. So the ROC is infinity, and the IOC goes from negative infinity to infinity. So this would be, this is the one case that we hadn't seen yet, right? We called this case 2. I do want to do a couple more examples, and I do want to do some trickier ones here. But this shows you that all three cases are possible, and it's really hard to tell before you do a problem which one it's going to be. Okay, let's look at number 5. This time our power series is going to be n equals 0 to infinity of -3 to the n x to the n over square root of n plus 1. You know, in the last problem when we did it, or 2 problems ago, I forgot to mention the center here, right? Remember, the center of this problem was 3. And for this problem we just did, the center was 0, right? It didn't ask us for that. It's always good to keep these things in mind as you do the problem, though. Okay. What about this one here? The center is 0 yet again, right? Because we have an x to the n. So let's begin with the ratio test. We're going to do the limit as n goes to infinity of the absolute value of -3 to the n plus 1, x to the n plus 1, over, when you plug in n plus 1 on the bottom, you actually get square root of n plus 2, times a reciprocal. We're going to get square root of n plus 1 on the top. On the bottom we get -3 to the n x to the n. What does this equal? -3 to the n and -3 to the n plus 1 leaves us with a -3. But when we pull out the -3, remember it's absolute value of -3, so we know we're going to get a 3 out here. What about the x's? Well, I have x to the n plus 1 and x to the n, so that's going to leave us with an x to the 1 on top. And that can come out, but we do need an absolute value for that one. And what do we have left in the limit? In the limit we have the square root of n plus 1 over the square root of n plus 2, or I'm going to write it this way. How do you take that limit? Well, let's go ahead and divide the top and bottom by the square root of n. We end up with 1 plus 1 over n over 1 plus 2 over n. What does this whole limit give you? This part right here is equal to 1, so you actually end up with 3 times the absolute value of x. So this series converges when 3 absolute value of x is less than 1. Now, does that mean our radius of convergence is 1? No, because we need to isolate the absolute value of x. Okay, you always isolate the absolute value part. And so if you divide both sides by 3, you end up with the absolute value of x is less than 1/3. This is the form that we want, and so this guy right here is the ROC, right? The ROC is 1/3. Now, we're not done because this is case, we called this case 3, right? This is case 3, so we do need to check the edges, okay? So let's go ahead and figure out the interval of convergence now. So we've already got the absolute value, or the x isolated, right? So we just need to check these edges. So let's do the edge cases now. Let's start with x equals -1/3. So if you plug in a -1/3 up top, you end up with the following. We get -3 to the n and then -1/3 to the n over the square root of n plus 1. But the top two guys multiply to 1, don't they? Because negative 3 times negative a third is just 1. So it's just 1 to the n. So what do we get? We get this. I want to show you guys a cool trick here. We could do a limit comparison test with 1 over the square root of n, but I want to show you guys something. If we use a trick called reindexing. Reindexing means that if I instead want to kind of start the count instead at n equals 1 to infinity, if I start instead at 1 to infinity, then that means this actually becomes 1 over the square root of n. Right? And notice these two series are identical, right? The left side, on the left one, the first term is 1, and on the right one, the first term is 1 also. So these are the exact same series. The only difference is the one on the right is I'm starting at n equals 1 to infinity, and the one on the left, I'm starting at n equals 0, but the actual terms are all identical. And so we could tell right away that this guy diverges. Why? Because it's a p-series, where p is equal to 1/2, which is less than or equal to 1. Okay? We always need to justify everything that we write down, okay? So it diverges there. Now, what about the case of x equals a third? So if you do x equals a third into the series, if you do 1/3 times negative 3, you actually get negative 1 to the n over the square root of n plus 1. This requires a little bit of extra consideration, so I'm going to do this on the next page. Okay, what I'm going to do is I'm going to use AST. So AST. So Bn is equal to 1 over the square root of n plus 1. This is AST. And so we need to check both conditions. First, I check that the limit as n goes to infinity of 1 over the square root of n plus 1 is equal to 0. That's true. And then notice that 1 over the square root of n plus 2 is less than 1 over the square root of n plus 1. In other words, Bn is decreasing. This one's easy. We didn't need derivatives to show that it was decreasing. So that's true. So by AST, this series that we just wrote down, it converges. Okay. And so we're ready to write down our answer. Okay. Our ROC, remember it was a third, and our IOC, remember we just determined that it diverges at 1/3. No, sorry, it converges at 1/3, but it diverged at negative 1/3. So the interval of convergence is negative 1/3, comma 1/3. Okay. Let's do one more example. I'm doing a lot of examples this time because I want you guys to see lots of problems here. So let's do another one. How about number 6? This time our series is going to be, or our power series is n times x plus 2 to the n over 3 to the n plus 1. Notice this time that our center is negative 2. All right, let's go ahead and use the ratio test, okay? So we're going to do the limit as n goes to infinity of the absolute value of, we're going to replace every n with an n plus 1. And this is going to be 3 to the n plus 2, right? We're replacing it with an n plus 1. So we get n plus 2. So times the reciprocal. This becomes 3 to the n plus 1 in n, and then x plus 2 to the n. All right, this is an plus 1 divided by an. So what does this become? Let's look at the x's. We have x plus 2 to the n plus 1, x plus 2 to the n on the bottom, and so we're left with a first power up there. So this is equal to, we know we have an x plus 2 up here, right? What about the 3's? We have 3 to the n plus 1 up top and 3 to the n plus 2 on the bottom. That leaves us with a 3 on the bottom, and that is not in the absolute value anymore because it's already positive. So we have this. And the only thing we have left in the limit is n plus 1 over n. Okay, we've done this before, right? This is x plus 2 over 3, limit as n goes to infinity. If we divide top and bottom by n, we get 1 plus 1 over n over 1. But this limit is 1, and so this just gives us the absolute value of x plus 2 over 3. So we now know that it converges when x plus 2 over 3 is less than 1. But does that mean 1 is our radius of convergence? No, because we need to isolate the absolute value. So if we multiply both sides by 3, this says that absolute value of x plus 2 is less than 3. So we just found our ROC, right? Our ROC is 3. Okay, now let's find the interval of convergence. We're going to write negative 3 is less than x plus 2 is less than 3. But remember, you have to isolate x to find the interval. So if we subtract 2 from all of these, we get negative 5 is less than x is less than 1. So those are our edge cases now. We have to check x equals negative 5 and x equals 1. So let's start with x equals negative 5. If you plug in a negative 5 into the actual series, we end up with n times. Negative 5 plus 2 up there is just negative 3 to the n, and the bottom is 3 to the n plus 1. Okay, what does this look like? So let me show you how I would separate this. So here's what I would write. I would write, you can break it off like this, and then the 3's cancel. So this is our series. Okay. This might look like a tricky series until you realize that this thing doesn't even go to 0, right? So let's use a strong divergence test, right? What would be the limit as n goes to infinity of the absolute value of that? That's just n over 3, which is infinity, which is definitely not 0. So it diverges. Okay. Now let's try x equals 1. Okay, so if you plug in x equals 1 into there, you end up with n times 3 to the n over 3 to the n plus 1, which is just n over 3. Again, if you use SDT on that, the limit as n goes to infinity of n over 3 is infinity, which is not 0, so it diverges. Okay. So we just found out that it diverges at both edges. So we're ready to write down the answer then. The ROC was 3, and the IOC was from -5 to 1 and not including either edge. So we need to make those an open bracket. Alright guys, I know this was a long video, but I hope all the examples were helpful. Thank you very much for watching.